everybody. So, as Noah said, I'm Mark. I'm a PhD student. I work with Christopher Carruthers in the high-performance computing area. And I'm going to be introducing NEMO, which is our neuromorphic hardware massively parallel simulation model system. And so in order to really kind of understand NEMO and what we're trying to do and what it's capable of, I want to go over a couple broad topics. First off, I want to kind of delve into parallel discrete event simulation, or PDES. Really brief kind of overview of what it does and what it allows us to do. I also want to talk about neuromorphic hardware. We've already kind of discussed that with the previous meeting. I want to kind of mention what makes neuromorphic hardware appealing for our research interests. I want to talk about the demanded potential for neuromorphic hardware, especially when it comes to supercomputing and high-performance computing systems. After that, we're going to kind of talk about some of the contributions of NEMO, like what NEMO brings to the table and what it's capable of doing. And based on that, we're going to go over some of the neuromorphic compute models. These are models that I've kind of gone over briefly last time. I'm going to kind of go into a leaky integrated fire neuron and a couple other models to just give an overview of what we're working with and what these things are capable of. And I'm going to talk about some of the features and future features of NEMO, stuff that we're really excited about with NEMO, things that it's going to hopefully solve and make available for people to use. Since this is a high-performance computing project, we have experimental results running it on the BlueGene so I want to share what kind of simulation sizes we've been able to get running with NEMO and what kind of performance we've been getting. And then we're basically just going to look at the future work, stuff that's kind of in the wings, waiting to be done for NEMO. So, really quickly, parallel discrete event simulation is a type of simulation used for simulating large models. Now, it's really applicable for models that have discretizable events. Some of the things that have been modeled with PDES include network traffic, congestion, downloading files across the internet, airports, and it allows us to simulate models that would be too large using a non-discrete type of simulation. Some of the big advantages include having computation only take place when events are received and processed. Some of the things you're going to hear me talking about with PDES and the type of simulation NEMO is include logical processes, physical processes, and events. And these are kind of the three conceptual terms that get thrown around a lot with this type of simulation. So a logical process is the basis for all of this type of simulation. Any sort of entity that is receiving and sending events or has a state will be modeled in a PDES model as an LP. These are the elements that are really being simulated and looked at. You can have one or more LPs running inside a PE, or the physical process. The PE is the actual computational system that's running on the hardware. This could be a thread or an actual physical process or an MPI process running across a cluster, but these are the actual things that are running and executing in real time and are running the LPs. Now, all of the LPs communicate by sending events, and these are messages that are passed in between the LPs that cause something to happen. If it was an airport, for example, an event would be a landing or taking off event. In the neuromorphic and NEMO models, these events include things like an axon message or a synapse message or a neuron output message. So I've been mentioning airports. They're a really great way to kind of logically think about LPs, BEs, and parallel discrete event simulations. Here we've got a happy little airport being simulated as an LP in one of these large simulations. And at T0, an airplane event happens. Now, T0 means time event 0, so this is the first event that occurs. And the airplane landing event is an event that's been sent from somewhere else and is reaching this particular LP in airport. Well, what happens at T0 is the LP will schedule any follow-up events, do any processing that it needs to do, and then move on. And in this case, if we were having an airplane land and then take off after a certain amount of time, we'd schedule an event for takeoff at time of I plus epsilon. Epsilon we use in this type of simulation to refer to a jitter. The nature of parallel discrete event simulation is such that we don't want events occurring at exactly the same time. This sort of thing results in non-deterministic behavior, which is bad for modeling and simulation. So that's the rough kind of idea of PDES. All of our PDES work here is done using ROS. This is Rensselaer's optimistic simulation system, and it's a PDES tool, PDES modeling system that allows you to create discrete event simulation models on large scales relatively easily. It handles a lot of the stuff behind the scenes for you. It uses, in addition to having kind of a conservative synchronization method, it uses an algorithm called time warp. And time warp allows for very fast simulations to happen with certain models. Now, again, I don't want to go too far into it because time warp is actually really complex. It manages a lot of the distributed system synchronization and serialization problems. So it's not a trivial algorithm, but the gist of it is that each PE processes events as fast as it can and really just ignores what's going on a global level until a message is received by that PE that's scheduled to happen in the past. So what happens at that point is the PE will start undoing state changes and rolling back events until the time has gone back to the point where it's received this message. And then it'll resume computing from that point forward. So generally with these models, you want to avoid rollbacks as they can kind of cascade out to other LPs and cause major chains of event undoing. Generally though, this type of algorithm results in very good performance and actually will help you find parallelism where you might not have expected it or realized you had it. Now, more interestingly, I would imagine to this group, the neuromorphic hardware that's available is absolutely fantastic. Noah actually discussed a bit of it last week, or not last week, but last meeting. But neuromorphic hardware allows for super specialized computation acceleration. It's excellent for finding patterns in data. It's great at machine learning tasks. Spiking neural networks and neuromorphic hardware are being used to do brain simulations and hopefully more and more compute acceleration tasks. The really interesting thing, to me at least, is the power requirements of a neuromorphic piece of hardware. Like for example, the True North chip that we have at RPI, which eventually we'll get to use, depending on how the export control rules work out, uses 65 milliwatts of power to run. And that's tiny, that's an insignificant amount of power. And with further revisions of this hardware, we're expecting this chip to be able to be put on mobile phones and embedded devices. I mean, the board that we got is really just, it's definitely designed like a Raspberry Pi. It's got little GPIO ports on it and things. So it's really great at being low power. Now, with this new hardware comes some challenges. The programming paradigm is non-von Neumann. This means we're probably not going to see a GCC compiler for True North in any time in the near future, though it would be kind of a nice tool. New programming paradigms are going to be needed. You have to think of it in terms of correlates, cores, neuron inferences. There's a lot of differences between standard programming and neuromorphic programming. IBM's luckily released a couple of really handy programming tools. It's given T out to developers of the True North board, which is a plug-in for Caffe, which constrains Caffe learning models to a model that is compatible with the True North hardware. And they've also come up with this idea of correlates, which are these object-oriented design patterned objects that you can stick into a True North model and run. So you can assemble larger programs out of these.
The thing about not having PCC, is it that it can't run C at all, or could only run C with a large slowdown, a large amount of overhead?
Well, it doesn't have a fetch execute cycle like the hardware does it. It really is just taking input values, integrating them, changing the internal state, and then outputting values. So it's fundamentally different than a standard processor. So to make a compiler for it that takes C would be hugely challenging. Because it would be
But like in the same way that you can run simulations of this on conventional hardware, you could like simulate the CPU on top of it?
Yeah, actually IBM did it kind of as a, I don't know, a sandbox thing. Like they actually built a computer model that ran on True North, and it was really slow.
Okay.
So if you approach it from like the standpoint of let's build a CPU on top of a True North or a neuromorphic hardware, it's going to run really badly. Like so, what IBM's been pushing, a lot of these software designers for this stuff have been pushing, is to think about it completely differently.
Okay.
Though a GCC compiler would be fantastic. That would be excellent. Did you have a question?
You answered it.
Oh, okay, cool. So, with these kind of issues of programming paradigms and software, new software design techniques, where's the demand, at least in reference to our research, in reference to NEMO? And it's really coming about because of the transition to exascale computing in high-performance computing fields. Exascale computing is going to be the next generation of supercomputers. Not the one that's currently being rolled out, but the one kind of after that, so a bit off in the distance. And just to give you an idea of the scope of this, Titan is just one of the supercomputers available in the US. It was released in 2013, and it's got 18,000 CPUs and 18,000 GPUs for acceleration. And when running, it uses 8.2 megawatts of power. But with those 8.2 megawatts, you get about 10 petaflops of performance, of compute performance peak. And Tahane 2 is the world's fastest supercomputer right now, and it's got 32K CPUs running on it, with various GPU and Intel accelerator boards. And it runs at 33 petaflops roughly peak, but when it's fully spooled up, it uses about 24 megawatts of power. So if we continue to build larger and larger supercomputer clusters with more and more nodes, the power constraints are going to just hit, and we're going to have a situation where we won't be able to electrically power our supercomputers. So new systems need to have fewer and fewer nodes. And a NASA vision report on the future of supercomputers suggested that by 2030, the cutting-edge supercomputers will have roughly 20,000 nodes. So in order to do this, supercomputer designers are working towards integrating accelerator cards into the systems. Now these are specialized accelerator cards designed for specific compute tasks. Right now the common ones are GPUs and to a lesser extent Intel P's. And GPUs are really great at certain types of parallel execution. They're very specialized, but you get more power or more compute power for electrical power out of these types of systems. So why not neuromorphic hardware as an accelerator card? I mean, these things use up almost negligible amounts of electricity. Sticking one or two in a compute node in a cutting-edge supercomputer would not adjust the electrical bill in any really noticeable way. And they're excellent at doing machine learning tasks and rather complex algorithms that standard CPUs are not so good at computing. So that's kind of where we're approaching the problem with NEMO. So we're looking at designing the next generation supercomputers, and we need to simulate. So right now we have simulation tools that allow testing of different supercomputer architectures and different network configuration topologies. And we use a tool called Codes for a lot of this. Now, Codes is a system kind of built on top of ROS that allows for simulation of large supercomputer systems. So basically, we're using our current supercomputers to design the next generation of supercomputers for us. And so what we want to do is put and attach a neuromorphic hardware simulator tool into this supercomputer tool. And if we do that, we need to be able to simulate different types of chips, different types of hardware, different types of neuromorphic configurations. It needs to be flexible enough that we can actually kind of experiment with not just what has been already fabbed hardware-wise, but also theoretical and new designs of neuromorphic hardware. So this is kind of where NEMO comes into play. Because NEMO is an open source neuromorphic hardware simulation model. And it's really designed to simulate neuromorphic hardware of various types and integrate with our supercomputer simulation tools. Now, NEMO has been implemented using ROS, which gives it this event-driven, massively parallel infrastructure. That means we can run large simulations of tons of neuromorphic cores on large-scale simulations. And because it supports ROS, it supports optimistic event scheduling and reverse computation, two things that make PDES simulations significantly faster. Again, we could really delve into reverse computation and PDES acceleration, but I don't want to. So, but if you're interested, we can go into that. So NEMO, one of the really exciting things that I think about NEMO is that it's open source, and we decided to make it open source completely. And my hope is that people will start to fork NEMO, apply it to projects that I didn't even plan on using it for, add new models, validate it against other things, really just kind of get up and use it. And this is in contrast to Compass, which is the neuromorphic simulation tool that IBM gives. And Compass is very closed source, very proprietary, and I don't think anybody here has access to it. I know you can't just download Compass and use it. So by making NEMO open source, we're hopefully providing an alternative to Compass that's more flexible. So the other thing that's fantastic about NEMO is that we can model flexible hardware configurations with it. So if you're interested in how true north would behave if the neurosynaptic core size was twice as large or tiny, or if you had 32 neurons per core but only 12 cores per chip, or radically different designs, NEMO can do it since it's all fairly modular and all implemented in software. And in fact, we can even simulate impossible designs.
Two questions. First of all, where do we find the source code?
Oh yeah, it's on my GitHub repo. And I had a link, but I broke it. So I'll pull it up at the end of the lecture. But yeah.
Second question, I guess, was can you actually use neurons in like other things?
Oh yes. Though right now we're working on optimizing it. Its memory footprint's a little big.
Gigabytes? Or
yeah, gigabytes. Yeah, no, it's not terabytes. Like I run it on a desktop to do debugging and testing. But like if you wanted to run a large simulation, you'll hit swap pretty quickly. But yeah, you can definitely play with it. You'll need ROS right now because it is built on top of ROS. But yeah.
So I can confirm ROS actually runs properly inside virtual machines. You can locate like multiple cores into it in a VM and it still works properly. Also, what does impossible mean in this context?
Oh yes, glad you asked. So impossible designs, I mean from an engineering and hardware standpoint. Right now there's a lot of research going on in integrating MEMS-Zister technology into neuromorphic hardware. HP labs are actually working on trying to develop a system that integrates this type of variable resistor technology on a chip to create new neuromorphic hardware, but that's not possible right now. And that would allow, say, these neuromorphic cores to have a non-discrete output. Right now, a neuron in the true north chip will output a 1 or a 0, depending on whether or not it's got a input or whether it's spiking or not.
But if you had denser memory, those could output floats?
Right. And you can also have possibly learning chips at that point, too. If you can go back and adjust the weights of the network at runtime, you'd be able to alter the way that the chip is running when it's operating. And that's impossible to do with the true north chip right now. And so stuff like that. Since it's kind of flexible, we can actually add new models.
So it's flexible enough to like assume higher memory density than is currently realizable, that sort of thing?
Yes, and assume different types of output fan-outs. Right now, due to hardware constraints, a true north neuron only outputs to one axon. And that's one of the kind of sticky problems with true north. It's the one output issue. And so with NEMO, you could have a neuron output to all of the other neurons. So but that's not possible in hardware right now. Yeah. So it's also large scale. Again, we're high performance computing research. So we've simulated 65,000 neurosynaptic cores on our Blue Gene Q supercomputer. And as we work on improving it and making it more efficient, we're definitely planning on seeing more and more scale-ups and larger simulations. And one of the things that I think is interesting, it's going to be the next feature of NEMO, is support for other spiking neural network models. We started NEMO with the IBM True North model because we've got the hardware, we've got an IBM simulator, we can do pretty good validation of the simulation model without having to use one of the other neuron models. We can actually check our accuracy pretty well. But we do want to integrate it with other spiking neuron models. The Iskovich simple neuron model and the Hodgkin-Huxley model are the two next ones we're going to be supporting. And since it's modular, the goal will be to have the ability to simulate hardware with multiple types of neuron models per core or even intra-core. So if you wanted a True North core and a Iskovich core and then some other model core all working together, you could build that sort of model and simulate it and see how it plays out, how it behaves. Now, I did just go into a little bit about mentioning Hodgkin-Huxley and the True North model and stuff, so I do want to go over the neuromorphic computing models. We kind of touched base on this last time, so I'm not going to go again too deep, but I want to cover some of the key differences between a artificial neural network as you think of it in machine learning versus a spiking neural network. So spiking neural networks are based on the artificial neural network concept. They're a third generation neuron simulation, so they're one after the multi-layer perceptron. They were developed to simulate biological neuron behaviors that were observed in the cellular level. But recently, neuromorphic computing and using spiking neuron networks has actually been shown to be viable for general purpose computing. Now, neuroscientists have been saying that it should be for a while because that's how we all learn, is through spiking neural network models, but actually using it in formal computing has been kind of a recent development. Some of the biggest differences between spiking neural networks and multi-layer perceptron networks really include really are about the concepts of time. A spiking neural network has time. There is a time value in there, and each neuron behaves and updates its state based on the incrementation of this time value. Neurons also don't need to fire at every time step. In a MLP, your neurons will be outputting some value every time you run the simulation. Spiking neurons do not output at every time step. They could be very quiet for as long as they need. And so the activation level, or the membrane potential, or the voltage, depending on how you refer to it, this value goes up over time as each neuron receives spikes. So it's much more of a discrete type simulation, or a discrete event simulation almost, compared to a multi-layer perceptron.
Do you know if the T thing considers this when it's converting
I don't. I've been trying to figure that out, and there really is. There's some IBM secret sauce going on there because they've got a way to convert an MLP to a discrete spiking neural network with constraints of the hardware included. And it's not, they don't have anything published on it, and basically, like when we were talking with the IBM guys, they said, use it and just enjoy the fact that it works. They showed it does work. I mean, we validated it using the MINST data, the character recognition data set, and it does work, but how it works is it's kind of a black box. But hopefully they'll release a paper on it. All right. Oh, and one thing I found interesting, the first scientific model of spiking neurons was developed in 1952 by Hodgkin and Huxley. That's the model I've been referring to. It's kind of the beefy model. It has a lot of computations per tick, but it is able to simulate or model almost all of the observed biological neuron behaviors. So it's a great model. It's not used a lot because it does require something in the order of 10 partial differential equations per compute cycle, per tick. So most of the time for large simulations this isn't used, but it is like, it's kind of the big one. And all of the current hardware that's being fabbed right now is using spiking neurons with an output of 1 or 0, and they generally use a very simple integration. There's no sigmoid functions, there's no smoothing of input. There's significant research, though, on improving this and adding new features and increasing the capabilities of the hardware. And this simple integration function is actually, almost all of it's based on this function. This is the leaky integrate and fire neuron. This is actually just the integration part of it, but it's a very simple integration, and it's actually the basis for the IBM True North neuron as well. And in this type of model, you've got a voltage which is set as V, a time step t, and all you do to integrate and update your voltage state is take the active states of all the input synapses, which here is represented by x of I. And x of I is a binary value, so it's either 1 or 0. If it's 1, that means that synapse is active, and if it's 0, it's not active. And s of I is the synaptic weight, and that's set at the beginning of the model. So you simply just take the sum of all of the synaptic weights for any synapse that is active and add it to your previous time step voltage and store that as your new voltage. So it's not a really complex model, and it's fairly easy to build on hardware. The leaky integrate and fire also has a leak function, and the leak function is simply just taking a preset leak value away from the membrane potential or the current voltage and storing it in the voltage. It's just a way for neurons to slowly lose voltage over time. Almost like a loss of memory type function. It's not terribly complex because lambda here is usually set as just a positive value. And spiking and reset is also simple. If your voltage is greater than your threshold, which is alpha, then you spike and you set your voltage to the reset value. Otherwise, you just do nothing and let your voltage increase. So with these...
In the leak equation, should that be b sub j of t minus 1?
No, it's of t. You take your current time voltage.
Okay.
Yeah, so there are some little tricky bits because you integrate first, update your current to voltage, then you leak during the same time step.
Okay.
So yeah, once you complete integration, you've updated your current times voltage, and then you apply a leak function which reduces the voltage by a certain amount. So if you didn't update your voltage in the integration, if there were no inputs, the leak would just slowly or quickly drop off your voltage. But if there were some integrations, the leak just reduces the magnitude of that. Yeah. All right, good. This is the whole leaky integrate and fire neuron model, and this is actually what True North is based on. The full True North formula, the full True North neuron model is actually pretty complex, and I brought some handouts with the full neuron model available if you want to take a look at it. It comes, like I've got all the definitions, and also there's a link to the description of the IBM True North model in that handout as well. But what you really should be aware of is IBM added a bunch of new features to the leaky integrate and fire neuron. The big one they added was stochastic integration functions. So this allows an IBM neuron to probabilistically integrate values. This is actually part of that secret sauce that's being used with T. They somehow use a probabilistic function when applying the constraints, when converting from a cafe model to a True North model. And again, the exact way they do it is still pretty, like I honestly don't know how they do it. They've got some, I suspect a couple things, but it's really just conjecture. But the probabilistic model allows for some interesting encoding and temporal data encoding techniques because you can have a probability applied to any sort of input data over time. They have also added new leak functions. These are really interesting as well. The negative leak is actually a really boring graph. It really just allows you to set lambda to a negative value, or actually you set lambda to a negative value, which results in the voltage of the neuron going up over time without an input. I know the name negative leak is a little counterintuitive. In the paper, I think they should have maybe called it a positive leak, but because that's what it does. A negative leak will slowly increase the voltage of a neuron over time. And in fact, you can have self-firing neurons that after so many time steps will send out a spike on their own without any external input. They also added divergent and convergent leaks. These are leaks that change based on the value of the membrane potential of the neuron. Divergent leaks simply act as a pull away from zero. So if your neuron voltage is at 0 and you have this type of leak function, the leak won't apply any value at all. If your voltage goes above 0, the leak will start applying a positive value and will push the neuron voltage away from 0. And if it's a negative value, if the neuron goes negative, the leak will push it further and further away from 0 to the negative sign. Convergent kind of does the opposite. It will try to keep the value of the voltage of the neuron at 0. So if you go positive, it'll apply a negative voltage, and if you go negative, it'll start pushing the voltage back to 0. So with just these few features, there's actually several more features, including negative integration or negative thresholding and more suppression type neuron behaviors that IBM added, but these are kind of the big ones. These are the major changes to the leaky integrated fire neuron. And with these changes, IBM's been able to add a lot of interesting biological behaviors. They can simulate a whole series of known biological functions with this neuron, which the leaky integrated fire neuron can't do. And I think the really, really important thing, though, with these changes is that in addition to being able to kind of qualitatively reproduce Iskovich's biological neuron models, these additions are able to really drastically improve the way the neurons in the IBM True North core handle memory loss, handle degradation of data, handle inputs and outputs. Like, it really makes these things a bit more powerful. And as I mentioned, I do have the full neuron model here if you're interested, printed out, because it's huge, and I really don't think a slide would be a good thing to have for this. All right, so NEMO implements the True North neuron right now and follows the True North hardware. And we did this in a couple really, I think, interesting ways. We used a heartbeat message system to handle this sort of implicit, or to create implicit synchronization. Most spiking neural networks have a synchronization to them since all the neurons are operating at a time step of t. All the neurons have to compute and send signals and do all their work at that time. So that really makes it hard to parallelize it, especially when you're using parallel discrete event simulation, because it would require a global synchronization across all the neurons. So by doing a heartbeat, what we can do is only update neurons that have had work done to them or need an update. We also had a problem with fan-out message, or with message complexity, since in NEMO, every single element of the True North core is an LP. We have simulated synapses, axons, and neurons. Broadcasting this many messages is actually a huge memory problem. So we used fan-outs to reduce the message complexity, where a neuron or an axon will send a message to a synapse, which will send one message to a neuron and then another message to another synapse. So rather than having an exponential amount of messages, we kind of reduced it down to a nice log number of messages. And we've got reverse computation, which really speeds up events and event processing. And I've got this rather large graph here for the implementation of a neuron and how the events unfold in it. And don't worry about reading it. I'm going to be going over this in small chunks, so I like to give the overview first. But I want to start with the synaptic integration. and synapse messages. Now, when a neuron receives a synapse message, it saves its memory, it saves the membrane potential, its current voltage, in the message for reverse computation stuff, and it actually integrates at that moment. So neurons integrate as they receive synapse messages. Rather than waiting for all of the synapse messages to arrive and then doing one large integration function, neurons will integrate on the fly. And this allows the neurons to kind of not have to worry about axons that haven't sent a message. Axons, or when a synapse doesn't send a message, there's no real reason to look at it or do the computation on it. And when the next step for a neuron that's received a synapse message is to send itself a heartbeat message. This is a message that says this neuron needs to possibly spike, do its leak function, do its reset function. You know, it needs to do some stuff before the next time cycle. There we go. And heartbeat messages. So every large tick, with our simulation, and if you do run Nemo, you'll notice that there is a time, an end time. The integer value of that is the actual number of hardware simulations that have been run, and the floating point value is the in-between work. The True North chip actually runs at 1,000 hertz, and in between each clock cycle, there's actually a lot of stuff going on. They generate random numbers, they do all the integration, all this stuff happens in between the clock ticks. And to sort of simulate that type of synchronization, we use the floating point numbers to manage the in-between work. And the heartbeat is the last stage of that in-between work. That's set to nearly almost a whole number. And when the neuron receives that, it starts processing its membrane, or it starts processing the reset, leak, and other functions. So one thing I should mention, the heartbeat message, when it gets received, it means that a neuron has had synaptic activity this tick, or it's a self-firing neuron. And self-firing neurons are kind of, actually they've been rather obnoxious to work with in the simulation because they pop up all the time. There's positive leak neurons, there's weird negative leak neurons with negative reset thresholds, and there's a whole bunch of other situations where neurons will just spontaneously start firing. And so we have to deal with those, and so those neurons will actually be just sending themselves heartbeats every tick so that they update their own state. But for normal spiking neurons, what a heartbeat message means is that I've received some synaptic activity and I need to finish that up. So once a heartbeat message has been received, it calculates the time differential, which is another kind of speed up feature of these neurons. And basically, if a neuron's been sitting for a while, not doing anything, it actually won't update its own state. And so if the neuron was created and started living life at time of 0, and then at time 30 got a synaptic message for the first time, it'll have to look and say, okay, it's been 30 ticks since the last time I've been active. I need to go back and calculate my leak values and figure out if I actually have to adjust any of my voltages. So the first step is to figure out just the amount of time that the neuron's been sitting there idle. And then the neuron will update its state. So it's just a simple loop. It goes through, and while the amount of time that it has been idle is greater than 0, it's true, the voltage gets updated, we run the leak function, and we calculate the leaks of the neurons this way. So this allows for neurons that don't get used in a model to just sit and compute and take no compute time at all, which really speeds things up, because in a lot of neurosynaptic models, there are a great number of neurons that are just idle. And so not spending any time looking at them really does help this simulation move along quickly. So after you get your leak calculated out, the neuron will then check its threshold, which is again just a simple, is my voltage greater than the threshold? And if it is, it goes ahead and sends out its output axon message. And then it does the reset functions. Now IBM added some more features with resets. There's positive, negative, and saturation resets, but they work similarly to leaky integrate and fire function. If you really want to get into how the neurons work, I do have the full model here, and actually I did bring a neuron simulator tool if you want to play with it after this. So we have an event flow system also that reduces that improves the performance, reduces computational overhead of a neuron in the simulation. And there's text on here, but you don't need to read it. It's more technical than is necessary. The bottom line is, for these 3 neurons and these synapses and these 3 axons, if during a time step there's only one message that comes in on axon 0, the only synapses that are going to be activated are the synapses in the column that is attached to that axon, and with each tick, they send out messages to the neurons that they're attached to. So this reduces the message complexity and makes sure that as little is as active as possible. So some more NEMO features, just in case you weren't sick of NEMO yet. NEMO's built on ROS, which makes it really fast, really powerful, and you can do giant simulations. And we're integrating it with supercomputer models and supercomputer simulation tools as we speak, actually. So this will allow NEMO to run within supercomputer designing tools. We are adding support for JSON and Python. My goal is to have NEMO accept designs of networks or designs of neuromorphic hardware through a standardized JSON interface, which will allow other tools to kind of talk to NEMO and hopefully broaden its utility. And we also want to have support through Python for input spikes. As of right now, input spikes are defined programmatically, and we're adding features to make it so that you could have a file that's output through a Python API that sets up the input spikes for the simulation. And that's something I haven't really touched on, and mainly because the feature isn't ready yet, but input and output is important for this type of simulation, especially if you're approaching this from I want to build a simulation of a brain type perspective. And so we're planning on having Pythonic support and Pythonic API support for putting the input spikes into the model, and having a more basic output for the output spikes, but it'll all be standardized and hopefully be easy enough for people to use. And I'm hoping it gains a lot of flexibility too. While it probably won't be happening anytime soon, it would be nice to have NEMO apply or be a plugin for tools like Pine, and possibly even as a replacement for TensorFlow for spiking neuromorphic models. But that's a little further down the road. But all these features are coming soon, and NEMO is going to be pretty awesome when it's finally ready for prime time. But until then, we do have the GitHub repo, and so if you want to poke at NEMO, please feel free to. Right? I won't be offended if you fork it and find that there's a massive problem with it, and it's actually treating everything like cows in your visual identification program. Right? This is a good thing. Now, since I am in the high performance computing field, I do have to show off some supercomputer runs. We've gotten 65,000 cores running on a full rack of Blue Gene Q, and this is a weak scaling chart. If you're not familiar with weak scaling is a way to measure the performance of a large program running on a supercomputer, where you increase the amount of work as you increase the amount of compute. So every time we increase the number of Blue Gene Q nodes, we increase the number of neurosynaptic cores being simulated. And the idea is that you want to have almost a flat line for the wall clock time, which is shown here in the bar chart part of the graph. Because since you're increasing the amount of work and increasing the amount of compute power at the same rate, you shouldn't see an increase in the amount of time it takes to finish the simulation. The blue and green lines here represent the amount of events being processed, and that's generally a good sign when they go up like that, based on the number of compute nodes and amount of work we're working with. So it's actually getting excellent weak scaling results, and that's a good thing. And we did a strong scaling experiment. And again, if you don't know strong scaling, it's related to weak scaling, but instead of increasing the amount of work as you increase the number of compute nodes, you keep the amount of work the same. And so here you actually see, this is the event rate, which is the number of neurosynaptic events and all the other stuff going on in the simulation. And it actually starts to flatten out at about 512 blue gene Q nodes. And what's happening here is actually we're hitting the limit of the breakdown of the problem. We are simulating 8,000 neurosynaptic cores, and so right here at about 512 blue gene Q nodes, we're kind of maxing out the amount of parallelism we can extract from this model. Kind of, I know it's funny, but the way I think about it is, if you go to a laundromat with a bunch of clothes, there's only so quickly you can do the laundry, even if you keep throwing more washing machines at the problem. Like, you can't get it done in 15 minutes if each washlet takes 30, even if you're using all of the machines. And that's kind of what's happening here. We only have this much work, and as we add more compute power, it's kind of leveling off. But we have larger workloads, and with larger simulation sizes, we should see an improvement up beyond 1024 nodes. So I've already kind of mentioned future work because I'm kind of excited about the future work for NEMO. So bear with me, but I do want to say we're integrating it with the supercomputer simulation tools. We're going to integrate it with other neurosynaptic spiking neural network simulation tools and at least make it usable for somebody who doesn't want to become a parallel discrete event simulation expert. And we really want to have Pythonic I/O. That's a big deal for a lot of people who want to use this, especially because this could be a replacement for Compass for the True North chip, and possibly even used for other neurosynaptic processor designs. If you have any questions, I'd love to answer them. I could talk about this a lot, but I really wanted to spare you the gory details of a parallel discrete event simulation implementation, so I try not to go too deep.
I was curious, whether you had any idea how much performance you're actually losing by simulating versus running it on the real hardware?
Oh, it's huge. Huge performance loss. While NEMO actually is faster than Compass, kind of, like that's a tough comparison to make, but it is a very quick simulator. It's still something like an order of magnitude slower than the hardware.
On what scale? Only one order of magnitude? That sounds pretty good.
It's very good, but it's way slower. It also depends on the actual model you're simulating. And that's one of the reasons why comparisons between NEMO and like Compass are difficult, because you can pick say a very sparse model with minimal input and output and go really fast. But it might not be an accurate representation of the actual performance. When IBM actually got real-time simulation speed with their Compass simulator by using 16 racks of Blue Gene Q and a very small model. Like the model complexity was very low and the input and output was minimal. Like it was not a complicated model at all. So we've been actually, all of our benchmarks are done using a identity matrix type model, where if a neuron receives an input from axon that's the same number, so neuron 0 receives an input on axon 0, it sends a spike. So by doing that, it makes the model, the event rate, fairly high, which adds a lot of complexity and possibly makes it less performant than if we were doing something more realistic. But it seemed like a good way to kind of just get it.
Like a worst case number?
Yeah, it's nearly worst case. If it was worst case, then the neuron 0 would spike whenever it received any axon message. That would be a huge, but that type of model really isn't realistic for what I've seen in True North. And sort of fan out stuff.
So it's not just slower, right? There's also power, right?
Oh yes, yeah, it uses up a ton more power. Like the electrical consumption, because it's running on a Blue Gene, is monstrous. And so the True North chip is definitely the way to go, especially if you wanted something embedded.
So this accurately simulates the amount of power that the chip, or the design that you're simulating would consume?
Not yet. That's going to be version 3, I imagine. It's something that people are really interested in, but it's extremely hard to get that information and accurately simulate it. I mean, you can kind of roughly guesstimate it, like do some off-the-cuff math to say, okay, my model generated this many spikes and ran for this long. what's an equivalent true north model do, and you can kind of gauge from that. But it's, especially because IBM's got some like baseline metrics. But to get a specific number, it's extremely hard. Like it's something IBM's been trying to do. IBM says run it, if you want to do it for their hardware, run it on the hardware and get a multimeter and actually measure it, like to get the power consumption. They don't even have an accurate power tool. Yeah. Yeah.
Any idea of the heuristic though? Like more messages is more power?
Yes. Yes, actually that, on the hardware chip, the more messages you are sending and receiving, the more electricity the system uses. It is significant. Also, the distance between cores that are being communicated with also affects that. The chip itself is laid out in a grid with multiple internal neurosynaptic cores connected to each other. So if you think of it as a matrix and you're at core 00 and you're sending messages all the way to core 255, you're going to transmit across a lot more of the chip, and it actually uses up much more power than transmitting to the neighboring neurosynaptic core.
So to the extent that you can make an algorithm communicate locally, you can optimize the power consumption?
Yes. Yes, so you want to be aware of where your communication paths are going. If you're trying to eke out every single milliwatt, like since it's such a small amount of power being used by this hardware anyway, optimizing it really just shaves off a couple milliwatts here and there. So it's, but yeah, for battery applications, you'd want to do that.
What about latency? What about latency for locality?
Now that's the nice thing. Latency is always the same. On the True North chip, it runs at 1,000 hertz to the outside world. Internally, it's actually doing a lot of stuff per tick. But it doesn't matter how you organize your cores and what crazy setup you've got, for your model, it'll output its ticks it'll do all of the outputs every tick. So that's actually set. In fact, they even talked about you can even overclock it a bit and get slightly faster ticks. But this is Iskovich's symbol model, which is similar to the IBM True North model. It's not the exact same one, but you basically can create, you have a membrane potential, you've got your recovery parameters, and you can kind of tweak the parameters and play with it. Now this one's actually open source. This is available on iskovich.org, and you can download it and play with his model. It's a variation on the leaky integrated fire model, kind of like the True North one, but it's much more accurate for biological simulations. And let's see if I lost it. So you can generate spikes for it and see how it behaves, and actually watch the membrane potential change over time. And these parameters are named differently on the Iskovich model than they are on the IBM model, but they're actually compatible with each other. You just have to map them. And the IBM model is just not running, so I'm going to say I've got the Iskovich model to play with. Similar. And when I get the other IBM model working, I'll probably just bring it to the next meeting if you guys really want to play with it, because it is kind of fun and it helps you figure out how to program individual neurons for the IBM True North chip. I don't know, would you guys be interested in me bringing that next time? Yeah? All right, I will do that. All right, well, thanks. Contribute to Neuromorphic.